Okay, equilibrium constants Kc and Kp, they're capitals. Okay, equilibrium constants Kc and Kp. Right, so if you take a reaction which is in equilibrium, for example, the Haber process, the Haber process is a good example. You can write an expression for Kc. Okay, so Kc is the concentration of the products, and because there are two, there's two ammonias, you put squared, concentration of the products divided by the concentration of the reactants. Square brackets means concentration. Concentration reaction times, we don't bother putting it in, but there is a times there, the concentration of the reactants to the power 3, because there's a 3 there. Okay, this is the expression to represent Kc. When you work out the numerical value of Kc, you have to work out the units. Each time the units have to be worked out. Okay, so when you work out the units, you just do the calculation again, but use units this time. So this is concentration squared over concentration times concentration to the power 3. To the power 3. Okay, so you just do it again, but you put the units in. So can you see there's 2 concentrations on the top, and there are 4 concentrations on the bottom. So we can cancel the 2 on the top with 4 on the bottom. Okay, so that leaves us with 1 over concentration squared, like that. Okay, because you've got 2 concentrations on the top and 4 concentrations on the bottom. Then we take the concentration up to the top line. Okay, concentration is moles per decimeter cubed, and when we take it up to the top line, the squared becomes -2. Okay, so it's a bit like 1 over 10 is 10 to the -1, or 1 over x is x to the -1. Okay, and then you bring the -2 into the bracket, so it'll be mole -2, and then what you're doing, you're timesing here, so it'll be dm -3 times -2 is 6. Now you can leave the units like that, but it is standard practice to put the positive indices first. So the units should be written dm6 mole -2. Right, and like I said, you have to work out the units for Kc every time you do this calculation. Okay, right, there are different types of equilibria. Okay, the type that I've drawn here is an example of a homogeneous equilibrium. That there is a homogeneous equilibrium. Okay, now homogeneous equilibrium means that all the species are in the same state. All the equilibrium species are in the same state or phase. Okay, so that's an example of a homogeneous equilibrium. Can I just point out as well, when you're working these values out, these are equilibrium concentrations, not initial. They're equilibrium concentrations when you're actually working this out. Okay, homogeneous equilibrium is when it's all the species are in the same state. When they're not in the same state, that is called a heterogeneous equilibrium. When the species, the items, the equilibrium items are in different states. Okay, so an example of that, for example, like if you take, I don't know, like if you take carbon solid and steam, okay, and you get carbon monoxide and H2 gas like that. Okay, that's called a heterogeneous equilibrium. Okay, now when you're writing the expression for Kc, it is assumed that the concentration of solids and liquids are constant. The concentration of solids and liquids are constant. Okay, and it is only in the gaseous state and aqueous that change, and these have already been incorporated. So solids and liquids, you know, solids are packed really tight together, and liquids, the atoms are packed really tight as well. So the concentration is constant, and they're already incorporated into the Kc. Already incorporated into Kc. Okay, so for the example of a heterogeneous equilibrium, you ignore the solids and the liquids. So if you were to write Kc, the expression for Kc for this, you would write Kc equals the products concentration of CO times the concentration of H2 over the concentration of H2O, and ignore the concentration of the solid. The solid is constant, the concentration, and is incorporated into Kc, a constant already, because a constant and a constant is just a constant. Okay, so you've just got to watch out for that for heterogeneous equilibria. Okay, right, now Kc. Now Kc, sorry, just go back a second. Kc is when the K is the equilibrium constant. C stands for concentration. P stands for pressure. Okay, so it's more accurate if your reaction is just with gases, it's more accurate to use Kp instead. All right, so like for the example I just gave a moment ago, the Haber process. The Haber process, everything is a gas, and it is easier to measure the pressure of gases than it is to measure the concentration. Okay, but you've got to also remember that the pressure is proportional to concentration of a gas. Okay, so if the concentration of the gas increases, the pressure of the gas increases as well. So they are proportional to each other. So when we have an equation with all gases, it's more straightforward to use Kp instead of Kc. And Kp is really similar. Okay, so it is the partial pressure of, and the way you write it is a small p, the partial pressure of ammonia. Okay, and that is going to be squared, because there's two of them, over the partial pressure of nitrogen. You just write the item in brackets, you use just normal round brackets, times the partial pressure of hydrogen, but it is to the power 3, like that. Okay, you work out the units in a similar way. The pressure might be in pascals, the pressure might be in kilopascals, the pressure might be in atmospheres. So whatever the pressure they give you, you work it out the same way and cancel out the pressure. Okay, so P here stands for partial pressure. Okay, now how do you work out the partial pressure of a gas? So the partial pressure of a gas, is the contribution that the gas makes towards the total pressure. Okay, partial pressure is the contribution the gas makes towards the total pressure. And the way you work out the partial pressure of a gas, so partial pressure of a gas, let's just say gas A, okay, this is the partial pressure, right underneath, partial pressure of gas A, okay, the way you work it out is you take the mole fraction of A, the mole fraction of gas A, and you times it by the total pressure. And the total pressure we say is a capital P. So my handwriting's not very good, so the little p, that's a little p, and that's a capital P. Okay, and the mole fraction, the symbol we use for mole fraction is X. Okay, so to summarize this, we could say the partial pressure of A is the mole fraction of A times capital B, P, the total pressure. Okay, so let's just break this down, what this actually means, right? So first, the partial pressures need to total the add up to the total pressure. If you have, for example, if you have three gases, okay, if you have gas A and gas B and gas C, you've got three gases in the equilibrium mixture. The sum of the partial pressures has to equal the total pressure. Okay, the sum of the partial pressures has to equal the total pressure. This mole fraction of A, of the gas, whichever gas we just called A, the mole fraction is calculated. You calculate the mole fraction of the gas. So let's just call gas A. Okay, is the number of moles of A over the total number of moles in the gas mixture. Total number of moles in gas mixture. Okay, so this is only used when everything is a gas in the equilibrium, right? You work out Kp rather than Kc. This is the partial pressure, so we're doing it in terms of pressure because it's easier for gases to talk about pressure rather than concentration of a gas, but they are proportional to each other. And the partial pressure is worked out using the amount, the mole fraction, times the total pressure. Okay, the mole fraction is the number of moles of the gas divided by the total moles. Okay, and then if you add the mole fractions together, so if you add the mole fractions, the symbol we use is X for mole fraction. If you add the mole fractions together, say if you've got mole fraction of A, gas A, and mole fraction of gas B, and mole fraction of gas C, then the mole fractions should add up to 1. So it's important you check your calculations to make sure that it does actually add up to 1. Okay, now when you do these things, you get your figures, your calculations, and work out your units each time. I'll just show you one more example though. One more example. If you have this, which is the decomposition of calcium carbonate, okay, with solid calcium carbonate, and it decomposes to calcium oxide, solid, plus CO2 gas. Okay, this is an example of a heterogeneous equilibrium, and heterogeneous, so the pen's not very good, equilibrium. Just be careful with your spelling there, that's an N. Heterogeneous equilibrium. Equilibria is plural, equilibrium is a singular. Now if we write the expression for Kp for this equation, we take the partial pressure of CO2, because it's a gas, and then because these are solids, solids and liquids are not included in their constant, so they've already been taken account of in the equilibrium constant. So the expression for Kp for this equation is just simply the partial pressure of the CO2. So that's quite an interesting example, yeah? And partial pressure can be in pascals, kilopascals, or atmospheres. Okay, now what does K, these Ks, what do they actually mean, right? If K, now Kc, Kp, they're both equilibrium constants. There are lots of other equilibrium constants like Kw, Ka, Ksp, which you're going to come across in the course as well. They're equilibrium constants. I'm just going to call them K, just for short, yeah? They act the same way. If K has a value of 1, what does that tell you about the position of equilibrium, okay? Because K tells you about the extent of the equilibrium. You know, how far the equilibrium has progressed, okay? The position of equilibrium. Okay, so if K is 1, that means that the equilibrium is halfway between reactants and products. It's halfway between reactants and products. You can change the pen, see if it comes up any better. Halfway between reactants and products. Okay, it's halfway between reactants and products. If K is a large number, okay, because that makes sense, because if K is basically products over reactants, yeah, and if they're the same as each other, then that will give you 1, okay? So if K is 1, the equilibrium is halfway between the reactants and the products. If K is a large number, maybe like 100, a large number, the magnitude, the size of it, then that tells you that there are more products in the equilibrium mixture. There's more products in the equilibrium mixture. There's a better pen. Okay, there's more products in the equilibrium mixture. Okay, and if K is a small number, like I don't know, like 0.01, for example, then that tells you that there's more reactants in the equilibrium mixture. More reactants in the equilibrium mixture. Okay, so the magnitude, the size of K tells you about the position of equilibrium, the extent of reaction. Okay, now what happens when we change the conditions? Okay, going back to AS, right? If you change the concentration, let's say you change the concentration of the reactant, okay, the position of equilibrium moves to minimize the change. That's Le Chatelier's principle. So if you change the concentration of the reactant, the position of equilibrium will move to the right. So what I'm saying is reactants going to products here, yeah? So if you increase the concentration, when I say change, I mean increase. If we increase the concentration of the reactants, the position of equilibrium will move to the right, okay, to minimize the change, right? If we increase the temperature, then you've got to take account of whether it's endothermic or exothermic. So if the forward direction is exothermic and you increase the temperature, the position of equilibrium moves or favors the endothermic direction. Okay, so the position of equilibrium will move to the left in this case, because the forward is exo, so the reverse is endo, and position of equilibrium will move to the right, yeah, to the left, sorry. Okay, now in terms of Kc and Kp, if you change the concentration, if you change the pressure, this has no effect on Kc. Kc and Kp as well do not change. The only thing that changes Kc and Kp is temperature. If you change the temperature, then Kc and Kp will change in value. Okay, also if you add a catalyst, as well, that will have no effect on the value, the magnitude for Kc, Kp. Okay, equilibrium constants are only constant when the temperature is constant. Okay, now the way to think about this will not get you, this answer doesn't get you any marks, yeah? But the way to think about this, to help you remember what's happening here, if you take, actually let's do it again, let's do the Haber process, for example, okay, which is negative, it's exothermic reaction, okay? Now, if you change the concentration of something, that is a one-off change, okay? You change the concentration, not in equilibrium. The position of equilibrium moves to restore the equilibrium, but it will come back to the same equilibrium position because the ratio is a fixed, this is a fixed ratio, 1 to 3 to 2, okay? So if you change the concentration, it's like you're doing a one-off change. It's not in equilibrium, it'll move to restore the equilibrium, but it will come back to where it was. Whereas if you change the temperature, you're actually doing a continuous change. You've changed the actual temperature of the whole reaction, and it has to find a new position of equilibrium. So you'll get a new Kc, Kp. It'll be a new position of equilibrium. That's the way you kind of remember it. That's not, that's not the way you explain it. So for example, let's just take one example here, right? So if we take, I'm just going to do one example. If you look in your textbook, there'll be loads of examples, but I'm just going to take one, all right? If you take this equilibrium here, okay, and let's say the equilibrium concentration of NO2 is 0.4 moles per decimeter cubed. This is equilibrium concentration, yeah? And then the equilibrium concentration of N2O4 is 0.01 moles per decimeter cubed. This is equilib concentration at equilibrium, yeah? So when you work out Kc, I know it's gases, but we can still work out Kc because we've got the concentrations. So Kc is going to be the product, it's going to be squared over the reactant. Okay, so Kc is going to be 0.4 squared over the reactant. And when you do that calculation, it comes out as 16. The units are going to be concentration squared on the top, concentration on the bottom. So cancel out one of the concentrations and you're left with concentration. Okay, so that's units, right? So that's Kc for that equilibrium, right? So let's say we take off the, remember it's in a closed system, this is happening in a closed system. We take the lid off and we add in some more N2O4, okay? We take the lid off, we add in more N2O4. So we now add in, we have got 0.02, we kind of double the amount of N2O4, right? It is not in equilibrium anymore, okay? If you work out this expression now, if you work out that expression now, NO2 is the same, right? Squared. But the N2O4, we've doubled it. Okay? We've taken the lid off and we've put more in. Okay? That now works out. If you calculate that, that comes to 8 moles per decimeter cubed. That is not Kc. Kc is 16. At equilibrium, Kc is 16. This expression now is 8. Okay, we need to restore the equilibrium. We need to make this 8 become 16. Okay, and so we need to make this 8 a bigger number. The way to make it a bigger number is to increase the top and decrease the bottom. Okay, that's what will make it a bigger number. If we increase the top, the amount on the top, it means that we are moving the equilibrium to the right. We are, sorry, my writing's gone terrible now. Move the equilibrium to the right. So we need to increase the top. We need more of this. More of this. So we need to push the equilibrium to the right. And then we need to decrease. We need to lower this. And then that will make the value become 16. Okay? So to return, so I'm going to write this down very briefly here. So the system is in equilibrium. The system is in equilibrium. Okay, you can work out the value of Kc. 2, maybe you double the concentration of one of the reactants, for example. Okay, not in equilibrium anymore. It's not in equilibrium anymore. Okay, you need to restore the equilibrium. Okay, the position of equilibrium has to move. Position of equilibrium moves to restore the equilibrium. Okay, restore the equilibrium. And in this case, we need to increase the Kc, so the position of equilibrium will move to the right. We'll move to the right. We'll move to the right. But Kc, the actual numerical value for Kc or Kp, does not change. The only thing that changes the value is temperature. Okay. Finally, for catalysts, catalysts increase the rate of reaction. Okay. Catalysts speed up the reverse and forward reactions by the same amount. Yeah. Catalysts do not affect Kc, Kp. So catalysts increase the rate of the forward and reverse reactions, by the same amount. Yeah. Does not affect Kc. I'm sorry, my writing is terrible. Right, now the tricky thing on Kp, the tricky thing with this topic is the calculations, yeah? So you need to practice lots of the calculations, lots of exam questions, and that's the kind of tricky part of it.